So is it hanging off the table?
I've got a giant table here with a hole in the middle. I have a string attached to the smaller mass, and the string basically comes down and it's attached to this 3 kilogram mass underneath the table.
Okay.
Not exactly the same thing, because I don't have a table that large, but. One that's actually attached here. Come on. All right. So right now, if I just let go of the string, this should fall. Now, there's friction involved, so it might not, but there we go. So they are not of equal mass. The gravitational pull on this is significantly more than this. It's enough to overcome the friction, kinetic friction. However, if I swing this around, it is possible for this to basically stay in equilibrium as that goes swinging around. Now, the difference between what I'm doing right now and the example I'm doing is that I have this thing spinning on a table as opposed to in air. In the lab, you'll be doing it in air. So the table is frictionless, which I can abbreviate as mu sub k equals mu sub s equals 0, shorthand for frictionless. And so this thing is spinning around, keeping this mass exactly where it is, in static equilibrium. So the question is, how fast does this need to spin in order for this to happen? That's the problem. So V equals what? So we start out with force diagram. What are the forces acting on the 1 kilogram mass?
Gravity. Gravitational force.
Thank you.
Normal force, I can know.
Tension.
Anything else? Okay. Yeah, that's it. The tension is the centripetal force in this case. So now, looking at the 3 kilogram mass, what are the forces acting on the 3 kilogram mass?
Weight and tension.
I'll call this weight 1 and weight 3. Just for the sake of ease, let's let the acceleration of gravity be 10 meters per second squared. We're on some strange planet where the acceleration of gravity happens to be exactly 10. So from this right here, I know that the weight is equal to 30 newtons. Therefore, the tension here, since this is in static equilibrium, if it's in equilibrium, the forces balance out. Force up equals force down. So that also has to be 30 newtons. It's the same rope, same tension. And so, plug in F equals ma. My centripetal force is equal to mass times the centripetal acceleration. This is 30 newtons. And that's equal to 1 kilogram times V squared over R. R being 2 meters.
How'd you get the rope equal 30?
I think it 30?
Does it have to
For the
be
road?
equal?
Is it cause that one's hanging off the table?
This is an
Yes,
equilibrium.
this is just hanging there, it's being pulled up by the rope and pulled down by the force of gravity. So its weight is 30 newtons, mg. And so the tension has to be the same because this is an equilibrium.
So the one touching the one on the table would still be 30?
Because it's the same rope.
Okay.
We're sticking with our traditional ideal rope. Same rope, same tension throughout. It's a frictionless table. Are you good?
Mhm.
Okay. Yeah, so this is something we found using the formula. This is something we found because of the situation. And this has to be the same value because of the ideal nature of that group. And so now we end up with, well, you need to get rid of the 2, so we multiply by 2. And so I have v squared is equal to 60. And so whatever the square root of 60 is. 7 point something. 7.73. Someone's about to tell me the real answer.
7.7459, so we can round to 7.46.
7.746
Yes.
units?
Miles per second?
Meters per second.
Meters.
Oh, yeah.
All right, meters per second. So that's how fast it needs to spin. If it spins faster than that, this mass right here is gonna start moving farther out because there's not enough force in order to pull it back in. So this will start to move farther out if it's traveling faster. But if it's traveling slower than that, it will start to spiral in towards the middle. And yep, there it is.
You said the rope was FC, right?
The rope was what?
The FC.
The FT is the tension in the rope. I just didn't do the force diagram where I included the rope.
No, not
also.
on the force diagram in the
Okay.
equation. FC.
Oh, yeah, that
That's the
is
rope,
the
right?
centripetal force, it's the force that's pointing towards the center, which in this case is the tension.
So going back to like the master set for the car, so then what's the centripetal force for that? For the car going around the curve?
So for the car going around the curve, all I ask for is the centripetal force, so it's mass times the speed squared divided by the radius of curvature.
Okay.
And I think I gave you all that information. All right, other questions before we take a small little break?
Wait, I don't think you gave us B.
We don't know what we're solving for?
Oh, yes, you did.
Okay.
In the question, sorry.
And I've made so few mistakes up till now, so I'd be shocked that I left something out.
Oh, no, you're good. It was in the question. It wasn't in like the original.
Okay.
So then what do you mean by if it's banked or not banked?
Bank, a non-banked road is just a normal flat road like this. A banked road is gonna be on the curve, so as you go around the curve like this, it's, the road has a tilt to it. It makes it easier to take the curve.
Okay.
And you typically bank it so that the normal force has some part in towards the center of it. So if I'm going around the curve, let's say overhead view, I got a track like this and I'm going around it. When the car is here, the bank should look something like that. So the car basically is going around the curve like this.
Okay.
I guess officially, that would also be a banked road, but that would be foolish if you're going around the curve like that.
So is it the same? Are the answer would be the same for banked and not banked?
I'd have to see the question again. So,
Okay. Is for A and for B?
curve is not banked, what provides the centripetal force? Oh,
Yeah.
So. If it's frictionless, well, what are the forces acting on the car on a banked road? Say it again?
The normal force,
There's one going that way, yep. And what's the other force?
gravity, or weight?
Okay. So those are the only two forces acting on it if it's a frictionless curve, a frictionless bank road. Again, I'm picturing the car on the sort of the right side of that curve. So the center of the curve is that way. The weight is perpendicular to it, so the weight cannot be contributing to the normal force there. The only force that has any part that is towards the center is that
So it'd be the normal force?
part of the normal force. But part of the normal force is keeping the car from, part of the normal force is up, which is fighting against the weight. And part of the normal force is to the left, which allowing it to go around the curve.
How would you draw that part of the normal force that's making it go around the curve?
How would I draw it? You typically look at the components. When I add forces, if I have a force going to the left and a force going up, then the net force is from where I begin to where I end. So that's adding forces. You can do the reverse process where I have a force that's going like this, and I want to figure out what do I add together to get that, where one of them is horizontal and one of them is vertical. So this is breaking a force up into its horizontal and vertical components.
And so its horizontal component is what makes it go in.
Yes.
Or block through.
That is the centripetal force, the horizontal component.
Thank you.
Is that unit of measure, newtons?
It's a force still, yes, it would still be
That's what I
newtons.
was thinking. And what did you say banked and non-banked mean?
Non-banked is a flat road, you're just going around, most of the streets around here. A banked road's gonna have a curve to it, so as you're going around the curve, you've got, well, basically, if you've ever seen, what immediately pops into mind is, at the circus, they have the motorcycles inside the cage, the round cage.
Uh-huh.
Because that's banked right there, it's the normal force which is pushing them towards the center, which allows them to actually, travel around.
So then,
Aren't racetracks like that?
yeah,
Racetracks also on the curves also have banks.
so then what's the difference when it's not banked?
When it's not banked, then I assume the center of the circle is that way. If I look at the normal force and the weight's still acting down, because down is defined by that. Normal force is acting up because perpendicular to the road is up. Neither of these are contributing to the normal force directly. Sorry, try that one again. Neither of these are contributing to the
Centripetal force.
centripetal force directly because they're both perpendicular to the actual net force. And so there has to be, if it's traveling in a curve around like this, there has to be some force acting this way. Because if you're traveling in a curve, there's gotta be a force towards the center of that curve, at least part of the force.
What would you call it?
Yeah,
I would call it friction.
so friction is what keeps it from,
Yeah, if you've ever tried driving around a curve on an icy road, you would know that
Oh, that's.
it's the friction that helps you go around that curve. Or lack of friction that keeps you from going around that curve.
So if it is banked, if it is banked and it's just a straight road, it's the normal force.
If it's frictionless, yeah, I can take, it is possible if the road is icy, if it's banked, I can still take it. If it's flat and it's icy, I have to drive real slowly in order to be able to take that. In reality, if I have a banked curve and friction, both, then I have, friction potentially is also helping me take that curve also. But the normal force is probably the main one. It all depends on what the actual angle is. and how fast I'm going. And if you take physics 151 or 251, you get to explore that. Brianna?
So when I was reading, it said something about, like being attracted to a really big building, like gravitational wise,
Okay.
and is there a gravitational pull between me and like, I mean, there is between everything.
Anything with mass.
Okay. Okay.
Which one are you on?
Or Newton was lying to us.
6.
It's just the smaller, I mean, it's not like you get up in the morning and start to walk out and that's probably not a good example because sometimes it is for pulling you back, but the gravitational pull of small objects is not keeping you here. It's not like you're leaving and there's a bunch of chairs following you, dragging you back. Those forces between you and all the other masses in this room is so incredibly small that we usually ignore them, but they're still there.
Yeah, number 6 is talking about between a person and a sandwich.
Now, in that case, you can't ignore it because that's what the question's asking, but it's why we ignored those masses or those forces in chapter 2 when we started doing force diagrams. Right, let's take a break. Take a 5-minute break, stretch your legs. I think today's free food is mashed potatoes, so I'm gonna go get some mashed potatoes and bring them in here.
How did you do that?
And, then we'll talk about the lab and other neat stuff like that.
That is